All right. Hi, everyone. So this is Team SimBot Dialog Management and Language Generation. Our team comprises of Nikhil, myself, Prasoon, Shubham Fal, Shubham Virmani, Shinhao, and Shinue. We are working with Professor Jonathan Bisk on the Amazon SimBot Challenge. I'll briefly go into what the Amazon SimBot Challenge is, with first presenting a quick video of what the environment looks like where we're working. So in this video, what we're looking at is a household environment. This is a simulated environment where a robot is moving, and based on the dialogues that are happening between two agents, a commander and a follower. The robot, being the follower, is carrying a dirty mug to the sink based on the commander's instructions, cleaning the mug in the sink, and making coffee. And then on the right side, the commander asks the follower to make breakfast, take a knife. So it finds the knife on a dining table, picks it up, picks the bread, and toasts it for the commander. So obviously, these household robots, they have many uses. Apart from these kitchen-like household chores, they can be used for search and rescue missions, etc. The Amazon SimBot Challenge itself was started in October 21. And it has two phases. First is the public benchmarks phase, which has three different tasks: CDH, TFT, and TATSI. And all of these three tasks are what we are currently working on. And then the second phase is a live interactions phase, where the commander will be replaced by actual human users of Amazon Echo Show devices. And based on our performance on the execution from Dialog history, our team has already been selected for live interactions phase for the next semester. So in general, the robotic assistant that we saw in the video, these are very complex undertaking. They require multimodal language understanding, language generation, management of dialogue and context, asking commander for clarifications. And these are the four language tasks that our team is working on. Further, we also require action mapping, and awareness of the environment, sequence mapping of actions, and trajectory planning. These are out of the scope of this presentation because another team, navigation and action taking, is taking care of those. With that, I'll hand over to Nikhil.
Hi, so I'm going to talk about the problem description specifically for our team, which is dialogue management and language generation. So our primary objective is to model two-way free-form dialogue between the commander and the follower. And this is done by performing embodied vision language planning, which basically refers to the bot performing various tasks based on the instructions given by the commander, grounded on the vision input that we get from the environment. This involves some core challenges. Since this is an underexplored field, there's a lack of generalizability, robustness, and simulator realness in comparison to the real world is also a concern. There are also no good natural language generation evaluation methodologies specifically for this task. Famous metrics like Blue and Rouge correlate poorly with human judgment, as they do not consider the semantic meaning of the words themselves. And we also have to handle ambiguity in instructions and implicit biasness in the pre-trained models that we use. So now I'm going to talk about the intended users for this project. SimBot is going to exist as a simulated agent in a virtual environment initially, and will be built according to the specifications provided by Amazon's internal SimBot team. They will be stress testing the agent according to the challenge and providing certification for it to be released as an Alexa skill later on. Once it is released as an Alexa skill, it will be available in all Echo Show devices to all the Alexa customers, and the customers will be able to use the bot in a game to solve mysteries and various tasks within a virtual environment. So that's how the bot is going to be stress tested. Later on, after the challenge, the bot is going to be available as an embodied agent with navigation and speech capabilities. It will initially be released to people with special needs and within industrial settings to provide assistance in various tasks. Later on, it will be available to general public for various household chores.
Okay, so our project is going to be based on the following hypothesis. First, the agent is going to use the past data, past game sessions, the observations, image, and dialogues as knowledge base to learn from it and infer the future actions. Secondly, the agent is going to model the other agents or participants' states by using the theory of mind models. And third, the generation of dialogues is going to be fluent and informative, just like natural language. And in our design, we're going to include the following features. First, the agent is going to understand the dialogues and generate actions from it. And secondly, they can understand the dialogues and resolve the ambiguity within it. And in terms of the generation, the generation of the dialogues is going to be informative. And fourth, in some cases, they're going to generate questions for clarification. And fifth, in some edge cases, they're also going to generate negative answers to deny some unnecessary instructions. And sixth, they're going to model the other participants and agent state by using this theory of mind model.
So being the language team of SimBot, we are mostly interested in everything that is concerned with NLP in this application. And the components that are highlighted in red in this architecture diagram indicate the components that we are working on. So firstly, we'll have the commander or humans interacting via Alexa with our bot. So the dialogue manager will analyze the commands that are given by the commander. And the dialogue manager has its own egocentric knowledge of the environment through its semantic map. It also has, it can also predict what's the user's knowledge of the environment through theory of mind modeling. Based upon this context that it has and the command that it receives, the dialogue manager will create a task definition, and the task definition can be further decomposed into sub-goals for action taking. Now, if the dialogue manager realizes that certain actions cannot be performed due to the constraints of the environment, for instance, the object is not present in the room, right? So in that situation, it has to ask follow-up questions or resolve the ambiguity. So it sends a representation of this unknown knowledge to the language generator module, and the language generator module is tasked with decoding different representations and either raising clarification questions to resolve the ambiguity or asking for alternatives to perform the action. Secondly, like the data set that we are focusing mostly on is Teach data set. The Teach data set contains 3,000 game sessions that model a commander-follower interaction. And the dialogues in this data set are unconstrained and not turn-based, which is pretty important. And yeah.
So for the resource requirement and constraints, we make use of the following data set, with the Teach data set being our main data set. And as for hardware, we utilize the AWS Cloud service, and we might also use the Amazon Echo Show devices in the future stage of the challenge. We also need access to AI Tutor and the other simulator environments as well. Also, we need to collaborate closely with the other team. As for design considerations, we make the following few assumptions. The first is the similarity between the real-world deployment environment and the AI Tutor simulator environment. And the second is the similarity between the real-world dialogues and the Teach dataset. And we have our AWS credits for development, and also we would use Docker container for deployment. We seek optimal user experience, and we hope to provide high performance at minimal cost. We also hope to support real-time interaction with low latency, which is the demand of our task. And due to the limited time, we just list the tools and dependencies of our project here.
So next we'll be looking at the test design for our system. We have divided our test design into two components. The first component is testing individual modules based on the module specific metrics. So for the object detection, we are using box average precision, where we test the precision of the boxes for each of the objects. And to test the fluency and the coherence of language generation, we'll be using standard metrics like Blue, Roach, BART scores, along with model perplexity. And for the end-to-end testing of our system, we'll be using Teach benchmark, two-agent task completion, which is basically the task of two agents, commander and the follower, completing a set of tasks while interacting with each other using natural language. For this task, we'll be using two metrics, task success rate and goal condition success rate. Here are some of the risks and challenges for our system. Firstly, our system requires a lot of pre-trained models in the pipeline, which might itself contain some biases and errors, which can lead to some propagation of these errors in our system. Next, our project relies heavily on third-party tools, which might constrain the actions of our system in the simulator settings. In terms of finances, our system requires training of large models on expensive cloud resources, which constrains our budget and enforces us to use the budget wisely. There might be some regulatory risk in the future when we want to explore the data which falls under some regulatory constraints. Here is the timeline for our project. So we have divided the project into 3 phases. The first 2 phases were completed during the spring semester, and the third phase we'll be working on in the fall semester. So first phase basically consisted of setting up the environment and doing literature review and documentation. We also did some analysis of the primary data set, Teach. And in the second phase, we worked on implementation of baseline models for individual modules of our system. We have listed 4 of those implementations here. And in phase 3, we'll be primarily working on improving individual system components and preparing for Alexa SimBot challenge.
Okay, now I'm going to talk about a few of the results that we obtained based on the various experiments that we performed this semester. As you can see on the left, the kind of Teach tasks that we have tasks like watering the plant, making coffee, cleaning all of X, and putting all of X and Y, etc. From the data set, we found out that the dialogue history and the corresponding follower subtasks were present in the data set. But like the environment state information was missing. We thought this is very important to determine the impact of every action that the follower takes based on the instruction given by the commander. So we had to manually replay the recorded games on the actual simulator, which is AI2 Thor, to get this environment information before doing anything else. As you can see in the figure below, if the instruction is serve 3 slices of lettuce on the plate, the subtask here will be pick a butter knife, slice lettuce, and place it on countertop. Subtasks are basically action and object pairs. Moving on to the state information that I was talking about, the state of the environment is represented by all the objects which are present in the environment and the corresponding properties of those objects. So here you can see in the first figure, we have objects like mug and properties like is filled with liquid, is dirty, stuff like that. So based on the subtask, which is fill mug here, we can see that the state changes from is filled with liquid for the object mug from false to true. We have this information for all the objects in the environment. Now, one application for this kind of information is to find the optimal and the minimal subsequence of tasks for achieving the particular goal. In the training set, we found out that there are a lot of unnecessary and repeated actions which are performed by the follower, even though they are not required. So to remediate this and get an ideal sequence, we created a probabilistic model of the training set subtask trajectories of any particular task type by fitting them to a hidden Markov model. In the HMM, the outputs will represent the follower subtasks. The states themselves are hidden, and our goal is to learn the probabilities of the state transition. After fitting the model, we sampled a few most probable trajectories and validated if the overall required environment state change can be obtained with these subsample trajectories. These validated subtask sequences can then act as ideal sequences for performing that particular task.
Next, we're going to introduce the intent classification, which is a core component, which is a component of our dialog manager. So end-to-end dialogue generation is indeed very demanding because the model needs to have informative dialogues with each other towards the completion task. So to add supervision signal to the generation model, we designed an intent classification task, which is a multi-label scheme, which means that each utterance can have multiple intents. Empirically, we find that the labeling to be very noisy because even for humans, it would be difficult. There would be variance in understanding the intents of the utterances in this dialogue. So altogether, we labeled 50 games, and there would be 673 utterances in total, and the average number of labels per utterance is 1.21. And here we illustrate how we compose in a single utterance. So a single intent. So an intent is composed of a dialogue act and optionally an object of interest, and also optionally something that is object specific. For example, the intent ask object location might be the follower asking the location of an object to the commander, and the intent informed task information abstract might be the commander giving instruction to the follower, which is an abstract instruction, for example, making breakfast. Yeah. And here we list the most frequently occurring intents and our labeled data. And for the experiments, we split the 50 label games into training set and evaluation set. And the model we use is very large uncased, and the input to the model is the utterance itself, as well as its context, which is just the previous few utterances in this dialogue. So this task is actually dialogue aware. And we have the results on the right. We can see that with only 35 labeled games, our model is able to achieve a F1 score of nearly 70. And we further break down the F1 score according to the ground truth intent class. And we can see that there's variance among the performance of different intent classes. And the model generally work well for the intents that are more frequent. And we also conducted our analysis of the model's predictions, and we find that models sometimes cannot distinguish between, for example, abstract task information and concrete task information, or the dialogue act, inform and specify. This is actually expected because there's noise in our labels. And so this means that the model actually behaves better than what the evaluation metric would imply. Yeah.
Coming to our retrieval baseline, we had two objectives. Now, our first objective was to given a commander question, we wanted to retrieve a similar commander question. And a second objective was given some context, and can we answer questions based upon that context? So we designed two different models for this. Our first model was to retrieve similar questions. For this, first we trained a command. First, we wanted to identify commands from the dataset. So we filtered our dataset by training a gradient boosting classifier on the NPS chat corpus and using it to identify questions. After this, we were able to filter out some of the non-useful sentences from the dataset and obtain only a list of questions. And then we fine-tuned DistilledBot for the retrieval. And you can see the results of DistilledBot on the right. So given a query like, is there a potato in the kitchen? We are able to retrieve similar sentences to that using a fine-tuned DistilledBot on Teach with very good confidence. And coming to the second part of our retrieval, wherein we wanted to answer questions based upon the previous context, we trained another baseline model, which is a dense passage retrieval. And what we did was, in order to do this, first we had to reorganize our data set a bit. And we converted our retrieval task into an open domain QA task, wherein we had the driver questions and the driver follow-up questions and the commander answers side by side, and the commander context, which is everything that the commander said before the driver asked the questions as the context. So based upon this, we fine-tuned DPR on our data set. And we were able to obtain pretty good results for retrieval. And you can see one of the example is on the right. For instance, suppose we want to know the location of, if the driver wanted to know the location of the knife, it can perhaps answer this from its own previous context. So as you can see that it's clearly answering that it's on the table, and it also gives the context from which it obtained this information.
Okay, so in order to understand the scenarios and generate informative dialogues from it, we're going to have an object detection module, a model that can search objects in the image from the text descriptions. And we evaluated one of the most representative model called MDATR. So MDATR works as the example on the right. So we evaluated one of the pre-trained MDATR model for phrase grounding on the data of the teach datasets, the images and sentences in game sessions. So we use the detection precision recall at IOU threshold larger than 50%, and true positive, false positive, and false negative rates for different object types as evaluation metrics. So here we plot the object types with the highest true positive, false positive, and false negative rates. So here are some findings and analysis. First, we can see that there are around 70 objects that the model can never detect correctly. One of the potential reasons is, of course, the vocabulary mismatch. And also, due to the nature of this model, there can be some random text span prediction, which makes up most of the false positive predictions. And also, the object detection performs worse when there are too many objects in the frame. We also suppose that the larger objects in the frames are easier for the object to detect, for the agent to detect. So we plot the relationship between the true positive detection rate versus the object box size. But we unfortunately we find no clear trend between these attributes. So in the future, we're going to integrate a model like MDATR in our dialogue management system. But there are some potential issues in it. First, since the model is not trained on hard negative examples, as an example on the right, it will also assume that the object in a sentence is going to appear in the frame. And also it lacks common senses, like the number of objects and object locality. But to be noted, most of the issues can be alleviated by fine-tuning the model in our game environments.
Building on top of the question, object detection, we have visual question answering, the VQA task, where we take an image and a question in natural language and answer it based on the image context. So for this, we trained a baseline NextMert model, which is a transformer-based model for the object detection as well as VQA task. And we fine-tuned it on our relevant teach data set. Here are some of the answers that we were able to generate from the image given and the question here. So, and here are some more sample questions. As you can see, that we were able to generate an answer with reasonable confidence.
So finally, we move on to one of the important modules of the whole dialogue management and language generation, which is the language generation unimodal baseline. So currently, we modeled the commander and follower dialogue utterances in a sliding window context using a GPT-2 based dialog GPT model. And we also model the perspective of a commander or a follower using techniques like attribute conditioning, which basically involves adding special tokens like commander and follower to the model during training time. And at inference time, it involves prompting the model to condition on those special tokens before generating the response. We fine-tune on 70% dialogues and evaluate our metrics for language generation on 30% unseen. And here's a qualitative analysis of our language generation model. So here we look at a commander asking the follower to make coffee. The ground truth is, let's say, done. Our fine-tuned model says, sure, where is the mug? Which is a perfectly valid response, given that this model does not know whether the action actually got completed or not. And that is a future uplift. Whereas the pre-trained model basically produces garbage. And why is it the way it is? Because it's pre-trained on social media data. Similarly, in this task, another conversation, our fine-tuned model asks whether it should boil potatoes with water, whereas a pre-trained Dialog GPT model will just produce garbage. So here's a quantitative analysis of our modeling approaches. Pre-trained model, as you can see, performs pretty bad on all metrics, including perplexity and Rouge. Whereas as we fine tune the model, add attribute conditioning to model perspective, and then add prompting to condition on that perspective while generating answers, we improve all of these scores. And it's a proof of concept that this works. So in a nutshell, for the next semester, our plans are to effectively integrate all of our work together. We have 6 individual pieces of work. We want to integrate in intent classification to develop a response strategy for the dialogue management model. We want to integrate object detection to, again, inform the entities. And we finally want to also work on F5 and F6, that major features that we mentioned earlier in the presentation, to incorporate user modeling and generating clarifications and denials. That's about it. Here are references. Thank you. And we're open for questioning, Q&A.
Really nice job, guys. It's a lot of expansive work. Are you have you split this up where you're kind of each in charge of one, or is everyone currently working on everything?
No, it's like right now we are working on individual components. So we have split up the work in that manner. Our plan for fall is going to be to work in integration, integrate all our individual components together.
And as to which components, we actually presented our own components. So Shubham worked on retrieval, and he worked on VQA, Benny worked on object detection, I worked on the language modeling, Nikhil worked on subtask extraction. We presented our own work in the results section.
So here's a question I have. When you're doing the training on the utterances and you weren't getting such great results, I wonder if, I'm assuming you were training on like 70% of just the questions, you were just picking those at random, and then the 30% test. So I wonder if there's some like stratification for task that might be important in that part.
A stratification might be important, but to be honest, I feel so we have got the whole dialogue, whole data set is about 3,000 conversations, and that makes our test set at about just 1,000, less than 1,000 almost conversations. And I have gone through them individually. Our responses are pretty good in the sense of they're very domain specific. Like, if the commander is asking boil the potatoes, the follower might ask where is the potato or where is the bowl to boil it in. So we have done a qualitative analysis of going through hundreds of responses, and they're pretty good. The fact that the scores are pretty low are more reflection of that, the fact that Blue and Rouge, they cannot as overlap metrics, word overlap metrics, they cannot capture the response being good enough. Like task please versus what should I do today, or do you have anything for me, all mean the same thing in this realm, but they would have like 0 Blue score.
Yeah, and to add on to that, as the games, like there are these 3,000 games that we have, and each of these games are independent games. So, even once we consider when we do the train test split, most of the tasks are covered inside the train split. So it's very rare that we would be finding a task that is not at all present inside the train split. Because most of there are very few tasks in the simulator environment, if you consider, and it's quite well represented in the training set.
Yeah, I guess maybe I don't understand enough about the structure of a game, but I was envisioning it being a set of tasks to complete a game. Is that correct?
Yeah. It's like every game session basically has dialogues between a commander and a follower, and the commander instructs the follower to complete a set of tasks, and the follower is responsible for completing them in the environment. And if the follower can't understand the commander, then he asks follow-up questions. So that's how the conversations are structured.
The raw data of each game contains not just utterances between the commander and follower, but at every time step, like at not every time step, but like at whatever time step is present in the game, there might be the task that got completed, or there might be the objects that got interacted with by the follower, or there might be what the semantic map of the follower currently looks like. So based, though all of those things, apart from other than the dialogue, all of those things can give us information like what is the task belief state, like what things got done or not, didn't get done. So what do we focus on next? And all of that can inform the dialogue model much more accurately, and that's what our integration plan of integrating all of our work is like.
Okay, it seems like there might be some, like almost if you trained on an entire game, like instead of training on questions, training on games might, because they're so similar, like I would think the tasks would be similar, right? And then it might, anyway, something to think about. Okay, when you guys were doing your custom tagging, can you go back to that part? You know what I'm talking about, where you guys were doing the...
Is it the intent classification?
I think so, yeah. You guys should have a minor point, always have slide numbers on your slides so I can...
Is it this one?
Yeah, I think so. So you guys were saying you manually tag these?
Yeah. 50 games
Yep.
and over 600 utterances.
Okay. And how did you guys do that? You just split them up, or what did you do?
Just put these dialogues into the Excel and label them.
Did you
Yeah,
like how many people were working on it, and did you have overlap and calculate kappa or anything like that?
Because it's an initial experiment, so
Yeah.
only one person
Okay.
labeled, and maybe in the future, if we want to like expand the labeling set, maybe we would have more people labeling the same task, the same data to ensure that it is consistent. But it's just a initial experiment.
Okay. It would also this would be an easy one to potentially move to Amazon Turk and have people do it for you.
I think so, maybe.
Yeah. So all right.
I think one thing to your earlier point, so the way the generative model is trained on games, so the work of Shubham presented on the retrieval baseline question and answers, those are actually across games. So it's all questions, all answers. And what we want to do there is like large language models, generative models, they might hallucinate information based on their pre-trained social media biases. So effectively, we also want to measure relevance using that retrieval model to kind of red team both models together to say, here's our generated output that might be more generalizable, but if it is not relevant, if it's not good enough, that's something the retrieval model can tell us. And like in that case, we don't have enough confidence to actually output something.
Okay. Yeah, I'm not necessarily suggesting that you should limit it to a game, but by just making sure like the test and train contain only whole games, the questions then might be closer, right? And again, you because you have such a limited number of games, you might miss some in your test and train. But I suspect the ones that you would get would be better because there are these, even in a more generalized task, there are these kind of types of tasks, right, where they're going to be doing similar stuff. That's just me hypothesizing. So I don't know much about this game as well, how they set it up, but long term, I think if you had lots of data, you would want to think about splitting it up. Okay. That's all I have. Any other questions from people there? There are lots of people there. I can't tell.
So,
No one there. Okay.
no other questions from us, Professor.
All right.
Right.
So I guess we're done and then we can move on to the next session.
Yep.
Thank you.
Thank you.
Good job, guys.
Thank you.